Welcome back. This is the final lecture for week 6, lecture 6B. We're going to continue on with mechanical considerations. In this lecture, we'll be looking at adding insulation to uninsulated piping. So a significant amount of heat can be lost due to piping that's uninsulated. The impact of heat transfer is dependent on where the pipe is running. If it happens to be in a conditioned space or in conditioned air, this increases air conditioning cost. Considering the piping might be for production. If the piping is an unconditioned space, then this lost heat must be added to make up for what was needed by the process. In this hand calculation, we'll be using a correlation method for the first time. We'll use a government-generated nomogram, or something called a nomogram. So what is a nomogram? A nomogram is a chart that contains a number of different variables. So what you've looked at already is we've been using primarily steady-state methods which reduce everything down to a single variable. A nomogram is an attempt to try to compile all kinds of variables in a simple chart or table that I can take a set of circumstances and apply them to this chart and come up with an answer. So the U.S. Department of Energy has a number of these nomograms for a lot of different situations, including piping heat loss, setback that we just did, boiler efficiency, etc. And again, all these quick methods are nothing more than screening methods to decide if more money should be applied to something prior to actually spending that time and money. Here's an example of a nomogram. This happens to be the nomogram to come up or to decide on how much heat is being lost due to hot water piping, depending on the type of insulation. Now this particular nomogram came out a little blurry because it shrunk down. But basically, the government put arrows in on the direction that you're supposed to go. So you start on the bottom left-hand corner. So the first thing you do is these are pipe sizes down here. So in their example, they have an 1.5 inch diameter pipe. When they enter the graph, they enter in and they start moving to the right, and what happens is you stop when you get the amount of insulation that you have starting with. So if my piping is uninsulated, I go all the way over to this. This is the insulation value for the pipe. In this case, it says none. I stop there and then I go straight up. These diagonal lines are the temperature within the pipe. So I stop at the temperature of my pipe. This happens to be 185 degrees. And then I move back to the left. Wherever I intercept over here, and this happens to be 1500, this is the number of BTUs per hour that I'm going to lose per each 10 foot of pipe. So I go across. I start with my pipe diameter. I stop at the current insulation value that I have. I move up until I hit the water temperature inside my piping. Then I move back to the left and it'll tell me what my heat loss is for a 10-foot section of pipe. So the energy savings calculation. Again, remember that the heat loss is from a 10-foot section of pipe. That's why they put 10 in here. Because if you go out in the field and measure your full length of pipe, the heat savings that you're going to calculate is based off of every 10-foot length. So they take your pipe length and divide by 10 to make sure that comes out right. So the heat savings will be, you're going to run that nomogram twice. Once with the current condition, let's say I have a bunch of uninsulated pipe, I can come up with a heat loss. Then I'm going to run the nomogram again with the quantity of insulation that I'm going to add on, let's say an inch. The difference is my heat savings. So I'm going to have a reduction in heat loss, reduction in heat loss. So it's a delta heat reduction. So in this example, I have a building located in Sault Ste. Marie, Michigan. Building has 180 feet of 1.5 inch uninsulated pipe. The pipe currently is carrying processed hot water at 200 degrees. Suggested that 2 inches of insulation be added to the piping. The boiler is 78% efficient, uses natural gas at 85 cents per therm. So from the chart on the back of the handout, and your handout has the nomograms included. For the heat loss for 1.5 inch pipe that's uninsulated at 200 degrees is $17.50 per 10 foot of pipe. Also from the chart on the back of the handout, if I insulate the pipe to 2 inches, now at 200 degrees, I've reduced my heat loss from $17.50 down to $100. This represents a delta heat loss reduction of 1650 BTUs per each 10 foot of pipe. So if we look at it, here's my 1.5 inch, uninsulated, come up, go over, 1750. Tricky on this second one, I go over to 2 inches, up, and you'll notice that the nomogram gets really tight down here. So it's sort of I know it's subjective, but again, remember these hand calculations are subjective. It's simply a screening technique. So the rest of the equation, I take my heat loss. This is the length of the heating season that I'm using this for, and I get that from my correlation weather data. When it is running, it's running all the time. 168 hours per week is all the time, times the cost of fuel, times the total length of pipe, divided by my efficiency, divided by how many BTUs per unit of energy up here. In this case, a therm is 100,000 BTUs, divided by 10, because I had 180 feet. This is how much heat I'm changing per every 10 feet. So this number really needs to be divided by 10. Savings $2,011.83. This ends lecture 6B. You now can proceed to assessment 6. Thank you.